Hello everyone, welcome back. In the previous videos, we looked at some of the key neural network architectures we have used for dealing with sequence data, from simple RNNs to LSTMs and GRUs. Now, before we go further, we need to answer a more fundamental question. When the data is actually text or language, how do we represent it in a way that these AI models can actually understand and then maybe build on top of it? Because whether we're building machine learning models, deep learning models, or even the large language models behind the modern AI systems, they all ultimately need structured numerical input. But see, text or language, by its very nature, is unstructured. So before we talk about more advanced NLP architectures like transformers, which we're going to cover in a later video, we first need to build this foundation clearly as to how we go from a raw text to a representation that a model can actually understand. So that's exactly what we're going to explore in this video. Let's jump in. So let's quickly see the different types of text that we can encounter, So depending upon the problem you're trying to deal with, maybe you come across the data which you have is related to journal articles, or maybe it's tweets, simple tweets, or maybe it's emails, or maybe it's some product reviews, or maybe it's medical records. You could have biomedical records, you could have clinical records, or you could have all kinds of data that is based on text. Okay, so but the thing is, for machine learning or deep learning algorithms, right, they typically expect, right, they need the data, in numerical format. So we need to convert this text data into some kind of a numeric format. If we can do that, right, then it's pretty much the same as how we do general machine learning or deep learning, right? So once the main challenge is to convert the data from this unstructured, right? What is the common for all this data, different types of text data you're saying? It's unstructured. It comes in different variations. So how do we convert this unstructured textual data into some kind of a structured numeric format? Right, that's the challenge. Once we do that, we can do machine learning. You can implement machine learning algorithms on top of that, or you can do deep learning on top of that. Okay, all right. So now let's talk about text representation in more detail. Meaning, how do you go from this raw text, right, to this structured numeric format? How do we go there? So there are three main things to consider. So the first one would be the word order. Okay, so how do you represent word order in a text? So what do we mean by word order? So let's take a look at a simple sentence. Teddy Roosevelt got a nice plush teddy bear. Okay, so as you can see here, right, there is a order in which these words are appearing, and depending upon the order, the words have meaning. So for example, Teddy in front of Roosevelt means it's part of the name, but the Teddy in front of the bear is this teddy bear, it's a toy. Right? And Teddy Roosevelt got a nice plush. So the plush is related to teddy bear. Nice plush and related to teddy bear. So there is a order, there is a sequence here, right? And we need to be able to represent this word order to correctly capture the meaning of the sentence or the text. Okay. So how do we represent this word order? All right. Well, there are different ways of representing the word order when it comes to doing NLP. One would be not representing the word order at all. Okay, so we can still do that. So obviously you're gonna lose some performance because, as you can see in this sentence, if you remove the word order and just so that's what this bag of words models do. So what the bag of word model do is it doesn't have a typical word order. So you break this text into individual words. For example, Teddy is a separate word, Roosevelt is a separate word. But when you do that, you'll have just one Teddy because you just broken down them into individual words, and you don't need two Teddys, one Teddy. But then you lost the context, right? So that's a problem with the bag of words models. But at the same time, they're very simple, right? So they're also, you can think of them as a benchmarking. So when you're doing some, building some system for, NLP, so maybe you want a benchmark model, you can use a bag of words model. So, and in fact, some simple tasks, even though there is no word order, the bag of words models, they ignore the word orders. They are still pretty powerful for very, very simple tasks. Okay. You can introduce some word order also to bag of words model using something called n-grams, but I'm going to talk about that later. But for now, think of bag of words models means they they pretty much kind of ignore the word order because they just break down the text into sentence, like, they treat them as a set of words. Okay. Then there is a proper way, the right way of doing, because you have to, when you're looking at the text, you want to treat the text as it is, right? Using the word order in which it's coming. So that would be sequence models. So sequence models, preserve the word order, in your textual data. All right. So within sequence models, there are different approaches. So on one end, you have the RNNs, LSTM, GRU. We have studied about these architectures in the previous sections extensively, and we have used them for the time series. So RNNs, LSTM, RNN, they were the first way, the right way of dealing with the text data. They were powerful at that time, but with the latest transformer architecture, right, they more or less got replaced when it came to the sequence data dealing with text. For time series and all that, you can still use LSTM and variations of GRU. They're still pretty solid there. But when it came to the text, the state of the art now has moved toward transformer models. So what is so special about this transformer architecture? Again, in the previous slide I showed you, right? Once in 2017, Google published transformer architecture, the BERT model came, GPT-1 came, and that just took off. Okay. So that's because the transformer architecture, right? They can do the context much more better. So what is this context? Again, this is just to show you the bag of word model. Just wanted to show you that, the words will get jumbled here. Okay, there's no particular word order. Okay, so going back to the transformer models, the biggest advantage of transfer models over, LSTMs or RNNs is their ability to capture the context through something called a self-attention mechanism. Okay, and they can also capture the long range dependencies much more better than LSTMs. Okay, so what is this context? Well, context, again, in the previous sentence also you can see, right? So Teddy, depending upon where it is occurring, it has a different meaning. Before Roosevelt, it has one meaning. Before, immediately before Bear, it has a different meaning. So just to show you another example, you can look at this sentence. Let him park the car in the park. So again, the same word park can have different meanings depending upon where it is occurring. So this is the context I'm talking about. So bag of words model, mostly the context is gone. You can incorporate the context to some extent by using something called n-grams, where you look at multiple sets of words. You can do that, but still it's still limited. So proper way of capturing context is to treat the sentences or the textual data as it is, as a sequence. And that's where, RNNs, LSTMs can do a good job for simple short sentences, but for more complex tasks or more proper way, transformer models completely dominate, right now when it comes to capturing the context. Okay. So word order, context, right? And then once you represent the text in a proper word order and using proper architecture with the context, right, then you want to convert this, unstructured text into structured numeric format. Okay. All right. So how do you convert this unstructured text to structured numeric format? Well, there are different ways of this numeric format we can talk about, like multi-hot vectors. So multi-hot vectors are particularly used for the bag of words model. Okay, we're gonna, again, in the later slides, I'm gonna show you what this multi-hot vectors mean. Or you could have something called one-hot vectors, or even better, embedding vectors, like word embedding vectors. Okay, so what are this multi-hot? What is this one-hot? What is this embedding vectors? Don't worry, in the next few slides, I'm gonna explain to you. Okay, but basically, when it comes to representing text, word order and context are the most important things. And the next big thing was this embedding vectors. Okay, so the state of the art right now is to use transformer models, and to represent each word in the text, we use embedding vectors, word embedding vectors, where each word actually has a numeric meaning. Okay, all right. Now, next talk a little bit about the text preprocessing. So see, whether you use bag of words models or the sequence models, right? Irrespective of what you do to represent your word order and context, all the text has to be preprocessed. So text has to be preprocessed first, irrespective of the type of models you choose. So what is this text preprocessing I'm talking about? Well, let me give you an example with a hypothetical dataset. So let's say we have a dataset which is a collection of tweets on Amazon. Okay. So again, these are just simple tweets. So let's say this is your data set, right? And let's say you have million tweets like this. Okay. So how do we pre-process this data? Again, irrespective of whether using bag of words model or sequence models, text pre-processing typically deals with three main steps. It's called vectorization. So you start with, you standardize, tokenize, basically clean and convert your raw text into some type of a structured numeric format. Okay. So what are these steps? First, what is standardize? So standardize could mean different things, or some or all of them. For example, convert lower or uppercase. So why would we do that? For example, look at this data set. Look at Amazon. So sometimes Amazon occurs with a capital A. Sometimes Amazon is like, everything is a lowercase. So it's the same thing, irrespective of the case. So you don't want your model to treat a capital Amazon and the lowercase Amazon as different. They're the same thing. So that's the first simple thing any vector standardization technique does, is to convert all the words in your data set to either lower or a capital case. Okay. And then remove stop words like, not that important words like A or E. So they don't bring much to the table. Again, some applications, stop words may be relevant, but typically you can, stop words can also be removed. And then about removing punctuation. Again, as long as they don't add much meaning to the task we are interested in, these can be removed. But again, there could be application like, the question marks might be important, or like, at the symbol is important, or some other punctuation is important, so we don't remove that. Okay. And then something called stemming. Stemming is like, reducing a big word into this like root single word. We can also do stemming. So these are all part of standardizing techniques. When it comes to bag of the words models, so again, we can use all of these, standardizing techniques. But again, when it comes to sequence model, definitely we convert to lower or capital case. But other than that, all the other stuff, removing stop words, punctuation, it really depends upon the particular task. And stemming is nowadays rarely used, when it comes to sequence models. Okay. Standardizing is just basically simplifying your vocabulary in your data set. Okay. So, once you standardize your data, each review in this data set has been standardized, then we tokenize. So tokenize, again, as the name implies, you're going to divide your text in each sample. Like, for example, for each tweet, you're going to break it down into individual tokens. So what are these tokens? Well, you could do different types of tokenization. You could do word level tokenization, like, break up basically each word in the sentence into individual words, like I promise that Amazon. It's straightforward to understand. Then you could also have subword level, meaning you're not only breaking your sentence into individual words, you're breaking them down into subwords. Okay. This is a more popular approach right now used in deep learning, again, in all the LLMs. It's subword level tokenization. You could also tokenize your data into character level. Basically, you just divide into characters and you have a finite set of characters. This approach is not much used anymore. Mostly, again, with the deep learning, you use subword level or word level. And then n-grams. So n-grams is like, for example, this word level, you're just breaking each sentence into individual words. But again, you're losing a lot here, right? Meaning, especially for the bag of words model. So if you're using bags of words models, right, using a single word by itself, right, or subword, it doesn't make, because you're using a lot of context. So if you are using bag of words model, word order is gone because you're treating that as a set, right? But you can still inject little bit of word order if that might help by using something called n-grams. Like in this case, I'm showing you bigrams. So I promise, Amazon Prime. So you use 2 or 3 word combinations at a time to bring some sense of word order and context. It's not ideal, but it's something. So n-grams is typically used when you use bags of words model. Okay. All right. Now, once you standardize, once you tokenize, then you convert your data to numeric format. So what format? Either it could be multi-hot or one-hot or word embeddings. Again, if you're using bags of words model, then typically we use multi-hot. But if you're using deep learning, the trend now is obviously to use the state of the art is going to be using word level embeddings, word embedding format. So what exactly it is, again, I'm going to show you in the next slides. So this is about text preprocessing. Irrespective of whether using bag of words model or sequence model, we do vectorization, that is standardizing, tokenizing, and converting to a numerical format. All right. Now let's look at the bag of words model. Okay. How does the actual final data set that structured numeric data set for a bags of words model looks like. How do we go from this raw text to this multi-hot numeric format? Okay, let me show you. So for example, our original unstructured raw data set looks like this. Again, it's the same thing. I just took the tweets of this for the Amazon. Okay, so what we do with the bag of words model is, so you look at each of this review, right? You standardized it, converted everything to lowercase, removed punctuation, stop words, and all of that. You did all of that. And then you tokenize. You broken down everything into words, right? Single words or two n-gram words, right? Once you do that, so into your entire data set, let's say you have a million tweets here. So in this entire data set, after standardization, after tokenization, you take all the unique words, and you put them into this column here, column names. So see what you're seeing here. So one of the unique word is Amazon, you put here. Maybe big was a unique word, never is a unique word, hypocrite, DVD, become. And as many unique words you have in your data set here, they could all become column names. Okay. So once you have all the unique words as this column name, now look at each tweet. Okay. So in this each tweet, right, is Amazon present? Yes, Amazon is present. So put 1. And then is the word big present in this tweet? No, 0. Is never present? Yes, see, I would never do such a thing. So never is 1. Is hypocrite present in this sentence? No, 0. Is DVD? Yes, so put 1. Become? There is no become here, so put 0. You get the idea. So once we calculate, we come up with this vocabulary of all the unique words in our data set, or also called corpus, right? Our entire data set. You take all these unique words and you make them the column names, and then you mark, looking at each sample in your data set, each tweet in your data set, and mark them either with ones or zeros, and you create this sparse data set. Okay, boom. But there you see what happened. So this is called multi-hot, meaning, many, in a simple sentence, many of these can be, ones, many of them can be present. Okay, but you see what happened. We just converted this raw, unstructured text into a structured numeric format for each sample, and then basically we did for the entire data set. Awesome. See, but the problem is, right, it's simple, but the word order or context is not preserved in bag of words model, right? It's treated as all these words are treated as sets. Again, as I explained, if you're using bag of words model, you can still use them, but to inject some kind of a word order or context. So instead of taking like one word as a column name, maybe you can take one or like 2 or 3 words together. So maybe Amazon Prime is a word, right? Or never do is such a word. Or online retailer is a single, column name. So you can take groups of words as your column names, and that will bring some kind of a context. Okay. Now, when do you use bags of words model? While it is very simple, right? Don't underestimate its power. Even though the word order is missing to some extent, you can, again, as I said, you can inject some word order with n-grams, right? By considering multiple words together. Bag of words can be pretty powerful, and they score pretty well on many simple NLP tasks, particularly like classification, sentiment analysis. They do an amazingly good job. So before going crazy, with sophisticated deep learning models, again, think about it. At least for benchmarking, right? Because if you're going all the way and building complex deep learning models for something like sentiment analysis, it should be better than, at least bags of words model. Okay, so consider bag of words model for simple tasks, and it can do a very good job. As the saying goes, right? You don't bring a sledgehammer to crack a nut. There could be, simpler ways like bag of word models. And as you will see later in this course, in the project section, you can see that, bag of words model can do pretty well for, generating sentiments, on simple data sets. All right. Okay. So this is with respect to the bag of words model as to how you represent. You go from raw text to multi-hot data set. See, once you convert your unstructured raw text into this numeric format, then from there on you can apply machine learning on top of it or deep learning. Typically, bag of words model, people use machine learning models. You can use deep learning too, but the main challenge here is going from this text to this numeric format. And this is how you do if you choose bag of words approach. All right. So now next I'm going to talk about sequence models. So if you use sequence models instead of bag of words, right, where you want to preserve the word order, how do you go from raw text to, I want to show you the final output. Like, let's say we want to create a one hot vector for each word in the sequence. Okay, what do I mean by that? Let me explain. So let's take a simple sentence. Okay, this is the raw text. AI race is on. Are you ready? Okay, so let's take this simple text and let's standardize this. Okay, so what do we mean by standardizing this? Again, as I explained before, you're gonna convert everything to, let's say in this case, we convert it into lowercase and we remove the punctuation. Let's keep it simple. Okay, we standardize the text. Then we're going to tokenize, meaning we're going to break this into individual words. We're going to keep it simple and we're going to do word level tokenization. So AI is a separate word, race is on, are you ready? So we have 7 words, 7 tokens. Okay, so the next step in sequence modeling is we take these words and we index them into integers, something like that. So we create token indices. So AI index is 3, race is 30, ease is some kind of a numeric indices. So how did we get these indices? Well, what we do is just like, in the bag of words model I explained, right? So you have all this raw text standardized and tokenized. So now this is just one sentence. So in my data set, there could be millions of sentences, right? And I have millions of these tokens. So I'm going to create a vocabulary. So I'm going to create a vocabulary of all these unique words after the tokenization. Okay, and typically what we do is we set a vocabulary size when you're dealing with sequence models, because the vocabulary can become pretty big. So there we kind of choose some kind of a cutoff just to make it manageable. So let's say we choose a vocabulary size of 10,000. So in our data set, maybe we could have 50,000 unique words, but we are saying we're going to cap at 10,000 unique words. And with that, what we're going to do is we're going to index each word. So maybe the letter A is 0, AN is 1, all is 2, AI is 3. Again, this is just a hypothetical indexing I'm showing you here. But basically, think of this as our vocabulary. Okay. Now you may ask, if we have 50,000 unique words and if we are capping that to 10,000, what about all those other words which will not, more than 10,000? So we use something called out of the vocabulary indexing for that. But don't worry about that at this stage. Okay. So for this stage, what we did was we standardized our text, we tokenized it, and based on all the unique words in our tokenized text in our entire data set, not just one sample, in the entire data set, we come up with a vocabulary size and then we index each word into integers. And that's what this looks like. Okay. So AI, race, is, on, are now, converted into numeric indices like 3, 30, 8, 11. Okay. All right. So now the next step is you take this token indices. Okay. Each token you map it or you convert it into a one hot vector. Okay. So what is a one hot vector? So one hot vectors look something like this. Okay. So I will explain. For example, take this 3. Okay. So what is 3? In the overall vocabulary, the word AI, its position, its index is 3, right? You see here 0, 1, 2, 3. So then we create a one hot vector. You create a one-dimensional vector of the size 10,000 because my total vocabulary is 10,000, right? So we create a one-dimensional vector of size 10,000 and we put everything 0 except the third position, because the third position corresponds to the word AI in the vocabulary. So that third position will be 1. So similarly for every token index. So we basically converted them into one hot vectors. So hopefully this clarifies you what we mean by one hot vectors. But boom, you see here, right? We converted this raw unstructured text into a final structured numeric output, which would be a one hot vectors. So each word is now represented by one hot vector. How many words we have here? Let's say out of all our sentences in this data set, we capped the sequence length also, meaning we say we want to cut off our sentences to only 7 words. So how many words are here? 1, 2, 3, 4, 5, 6, 7. Let's say we want to keep this size also fixed. So even if you have big sentences, you're going to cut them into 7. What happens to the remaining? Again, don't worry about that at this stage. So I'm just trying to show you how this sequence model looks like. In a very simple way, I'm trying to make sense. So let's say you have 7 words here, and let's say all of your sentences are 7 words, okay? And each of this word in your sentence is been converted into this numeric, one hot vector. So then your input data is now basically 7 by 10,000 matrix. So this is your input data, okay? So if you choose to use sequence models and you want to represent your data as one hot vectors, this is how you do it, okay? So, but most importantly, the current way, the latest way of doing, where you want to capture the syntax, not the syntax, the context and the meaning of each word. Because right now, see, there is no, this one hot vector, there's no meaning here, right? It's just saying, whether the word A is present or not. It's a different way, compared to multi-hot. It's a different way of showing that AI word is there. But how do you represent that AI word, right? This one hot vectors are not doing that. All they're saying is whether these words are present or not. Okay, but a better way of representing raw text in sequence model, converting this raw text, is to use something called word embeddings. So what exactly are word embedding vectors? Okay, word embedding vectors, I will explain to you in the next slide. So what exactly are the word embeddings? So see, instead of representing each of this word by this numeric vector, simply indicating whether that word is present or not, what if we can come up with a separate language, let's say, a numeric language that can map every word in human language into some kind of a meaningful numeric output. So, with that idea, let me show you what I mean. So word embeddings, again, they are numeric vectors, that can represent individual words. Let's keep it simple. So let me show you, this is a word embedding vector for different words, like in biomedical, or biology, or like in clinical, in 2 dimensions. So what you are seeing here is, if you see, we have represented the word heart in 2 dimensions numeric output. Okay, so if you see, each word has been represented here in these 2 dimensions, and as you can see, heart, lung, fever, lung, liver, kidney, brain, they're all together, meaning, because they're all like, body parts, they're all anatomical parts. See, that's what if we come up with a language, numeric language for words, what does that mean? Similar words should be located in the similar space, right? Like, for example, the word dad and father mean more or less the same. So if you're representing dad and father in a 2D plot, they should occupy the same space. If we have come up with a good numeric mapping to these words, right, then they should fall in a similar area in a plot. That's what you're seeing here. You can see all these words, that similar words, right? For example, the body parts are together. Similarly, all kinds of, other stuff like, nephrology, pulmonology, radiology, they're all also falling, in a similar, they're segregated, they're grouped in a similar, closer area. Okay, so hopefully this is giving you an idea as to what we're doing here. We're trying to come up with a numeric representation of individual words that give meaning to them. Similar words should have similar numeric representation. So let's see another one. So now let's say we're looking at word embedding vectors in 3 dimensions instead of 2 dimensions. So this is just a hypothetical word embedding vectors here. So again, you see dog and cat are placed closer to each other, right? And queen, women are kind of closer. Car, bus are closer. Orange and apple, which are fruits. So I hope this is making it clear what we are doing. So we are kind of coming with numerical definitions to our words, where similar words should have similar numeric definitions. Okay. Now, in practice, when we use word embedding vectors, we don't use 2 dimensions, 3 dimensions. We use much higher dimensions. So just to show you the concept, I'm just showing you these hypothetical ones. What about 10 dimensions? Right? This is how a 10 dimensions would look like. Like, for example, if you want to represent apple, the word apple, in a numeric fashion in 10 dimensions, so you can use all these numbers like 0.81, 0.02. So basically, whenever you want to use apple for machine learning or deep learning, simply use this numeric vector with values 0.81, 0.02, all that. Similarly for orange, similarly for banana, all these words, you can come up with some kind of a numeric representation. The only thing is, similar words will occupy similar positions in those dimensions. Another thing is, each of this dimension could mean something. Like for example, first dimension maybe the food. Is apple a food? Of course. So if with this dimension, you see the score is very high, 0.81. Royalty could be another dimension, right? So apple has anything to do with royalty? No. So the value is very low. Gender, low. Financial, natural, activity, power, liquidity, durability. Yes. See, again, apple could be durable. So, it might be there. If you keep it on the shelf, it's okay. So maybe the durability value is high. Again, these are all hypothetical sample word embedding values I'm using here, just to highlight the point and give you an idea as to what these word embeddings are and what these different dimensions could mean. Okay, so these word embeddings are calculated in a different ways. So you might be thinking, wow, this is awesome. How do we come up with this word embedding vectors? How are you coming up with this numeric language, numeric representation for each word, where similar words should have similar numeric representation? Well, there are two ways we use these word embedding vectors. One would be people have already come up with some pre-trained models, right, where they have, developed these word embedding vectors by training them on vast corpuses. Okay, so there are some pre-trained word embeddings which you can directly use in your models. You download these pre-trained word embeddings, and then whatever, once you have your textual data, right, standardize it, tokenize it, and once you have all these unique tokens, each word you just look up in that dictionary or whatever the database you downloaded your word embedding, pre-trained word embedding vectors, and then you can use for that word that numeric representation. That's one way, right? But see, again, as we learned, the words can have different meaning depending upon the context. So if you take these pre-trained word embedding vectors, they are static. The word embedding vector, once you take them, from these pre-trained models you download and use in your model, they don't change anymore. But we have seen that depending upon, like the Teddy Roosevelt has a nice plush teddy bear, depending upon how you use the word in the context, its meaning differs. So, right, for that, then we don't use pre-trained word embedding vectors. Then we can actually calculate these word embedding vectors as part of our training process. I will explain to you shortly. But in that way, all of your words will have, a numerical representation based on the context in which they are appearing. It almost all sounds like magic. See, that's again the beauty of NLP. Okay. So, all right, just wanted to give you an idea as to what these word embedding vectors are. Okay. In practice, though, when we use word embedding vectors in our deep learning models, instead of 2, 3, or 10, we use sizes of 128, 256, 512, or 1024. The more bigger models use, much higher sizes. Okay. Hopefully, this gives you an idea as to what word embedding vectors are, right? How we use them to represent individual words in human language. All right. Next, let me show you now. So if you want to again use sequence model, you want to go from raw text to word embedding vectors instead of one-hot vectors. How does that look like? So again, you can start something like that. It's the same thing what we saw with the one-hot. So you have this raw text, you standardized it, you tokenized it, and you have the token indices. And so again, I'm just showing you still the one-hot vector. So this was the one-hot vectors which we saw in the previous slide. But if instead we use the word embeddings, this is how it's going to look like. So for each token now, we have this, a numeric representation, more meaningful representation, either pre-trained word embeddings, or you can, so if you are not using pre-trained word embeddings, then there is a technique. Then what we use something called word embedding layer. And these word embeddings are calculated as part of the training process, right? And then they will be even more contextual. So the word embedding vector for each word then would be, based on context in which the word is occurring. Okay. All right. So we still have a vocabulary size because for indices, right? We need to create token indices. So all the unique words, you create a vocabulary size, you cap it to some size, let's say 10,000. So we use that and we create these token indices. Then, but in addition to that, now we also have to choose a word embedding sizes. So what kind of embedding size vector we want to use for each of our tokens? So 128. I'm just giving you the samples. You could use any word embedding size. Okay. All right. So this is how you represent raw text, for sequence models and especially with word embeddings. Next, okay, one more thing. So now the matrix, this is going to look like, 7 by 10. Say previously when we were doing this one. So when we're doing the one hot vector, you see, it's a 7 by 10,000 matrix. So it's going to be computationally more challenging, more complex. But when you go to the word embeddings, right? When you go to the word embeddings, it not only gives you more meaning to each of your word rather than simply using a one hot vector, right? You're giving more meaning, but your size is going to be much smaller. So here I'm just showing you because it's a 10-dimensional vector, I said 7 by 10. But in practice, this could be like a 7 by 128 or 7 by 256. It's much smaller than 7 by 10,000 for the one hot vectors. So word embeddings are very powerful, and that's the latest state of the art as to how we do, how we represent raw text. We use actually contextual word embeddings where each word brings significant meaning to the table, and that's how it has enhanced the performance of the modern day deep learning models that are doing NLP. Okay, all right. So now that we have seen how we represent the text data into numeric format, we have seen it for both bag of words models, and we have seen for the sequence of models. For the bag of words model, we use multi-hot, right? For the sequence model, we use one hot vector or word embeddings. Okay. Now let's look at the actual architecture. So neural network architectures. Okay, all right. So we can use a dense network, particularly for bag of words model. Okay, so again, for bag of words model, remember, so this is our raw unstructured textual data. We have vectorized this into a structured multi-hot data set, right, where each review has been converted, or each tweet has been converted into numeric format, right? And again, imagine, let's say we have a vocabulary size of 10,000. So there could be 10,000 unique words here, okay, and 10,000 values here filled with ones and zeros. So that's your single sample, right? So you take this numeric output filled with ones and zeros, right? So let's say the total vocabulary size is 10,000. So you take this, one-dimensional vector for each tweet, right, of the size 10,000. And you can pass this into a dense network. So take the single tweet, right? And again, so you can see here. So take the single tweet, right? This numeric format of the single tweet, which is kind of, 0 to 10,000 elements, let's say, right? So you take this 10,000 dimensional vector, and on top of that, you add a hidden layer. Remember, we have studied the dense networks. You add a hidden layer with 16 units, let's say. And on top of that, you can build another dense layer with a single unit to predict the final classification, the Y. Okay. All right. So this is a simple, bag of words based model. And if you're using bag of words, you can use a dense network. Okay. All right. Now, what about for the sequence model? So for the sequence model, you could have one hot vector or a word embedding vector. But let me just show you how a one hot vector by LSTM architecture looks like. So again, this is for sequence model. So if you have a sequence model, let's say we have a simple, this could be a RNN or LSTM or GRU, but let's say this is a bidirectional LSTM layer. Okay, we have already seen, these kinds of layers in the previous section. We have seen this, right? So again, this is a sequence to vector, because let's say we are going to use it to predict the classification of the tweets, whether the tweet is positive or negative, right? So for that, again, we have all these time steps. So let's say we have 30 words in our sequence. So each sequence in our data set is 30 words, let's say. Okay. So at each time step, we don't output anything, right? But whatever you calculate at each time step, it is fed into the next time step and next time step. And finally, at the last time step, we can add another dense layer with one unit, as you see in green, and that would be your final prediction, right? Where like whatever you are trying to calculate. Let's say the sentiment of this sentence. Okay. So again, remember, how do we calculate, the outputs here? You will guess the weights, the weight matrices, right? You guess the weight matrices, you will compute the output of each time step, right? And you feed it to the subsequent time step. All right. Now, what about each of this input word here, okay, in the sentence? So let's say this is my sequence. The movie is not, and there is a bunch of other words here I did not show you. And then the last word is good. Okay. So how do you represent each of this word? If it is a one hot vector, we already seen how the one hot vector looks like, right? This is how the one hot vector looks like. Okay. For each word. And there you go. So you took your, raw text, you converted, you have standardized it, all of that. I should have shown you here, but you standardized, you have tokenized, you have standardized, you have tokenized, and then you converted it into a one hot vector, each word. Okay. And if you do that, this is how it's going to look. Your architecture is going to look like. Now, if the vocabulary size, again, let's say 10,000 total words, the input X will be now a 30, because you have 30 words, 30 by 10,000 matrix. Each word is represented into this 10,000 size, one-dimensional vector. Okay. All right. Now, if you're using word embedding vectors instead of one hot vectors, and again using a bi-LSTM, bidirectional LSTM layer, again, this is your bi-LSTM architecture, and this is your words in the sentence, and then each word now instead of one hot vector, you can represent this with a word embedding vector. And this is how, you can represent it. And again, if you choose a word embedding size, let's say 256, then, each word is represented by a 256, vector. And then your input size will be a 30, because you have 30 words, by 256. Again, the movie is not blah, blah, blah. There might be many words here I have not shown here. The last word is good. Okay. All right. So this is a brief introduction about NLP and the modern or the latest way of doing NLP. I have shown you the fundamental things, right? How do you represent a text? The word order is important, the context is important, and if you ignore the word order, you can use bag of words model. If you want the word order, you use sequence model. And then for the final output, the numeric output, if you're using a bag of words model, you use multi-hot. But if you're using sequence model, you can use a one hot vector or word embedding vectors. And the latest way, the correct way, if you want state-of-the-art performance, we're going to use word embedding vectors. All right. So in this video, we built a very important foundation for dealing with text or language data in AI. We started with the core challenge that text or language is primarily unstructured. But AI models, on the other hand, again, whether machine learning or deep learning, they need their input to be structured and numerical. And then we explored different ways of representing text, right? From simpler approaches to more meaningful representations. And how these different representations can actually be used as inputs, again, to machine learning or deep learning models. We also saw how these representations connect to real neural network architectures, from dense networks in simple setups like bag of words, or to sequence models like RNNs and LSTM, where word order and context start to matter, as they should. So at this point, hopefully, we now have a clear understanding of how text is converted into a form that AI models can actually work with. But see, even with these approaches, there are still limitations, especially when it comes to capturing context efficiently over very long sequences, and most importantly, scaling these models. And that's exactly where one of the most important breakthroughs in AI comes into the picture, the transformer architecture. In the next video, we'll start exploring how transformers address many of these challenges and how they form the foundation of ChatGPT, Cloud, Gemini, or any other LLM and agentic systems we're currently witnessing. So please stay tuned and happy learning.